So today we're happy to have our own Gaku Liu, and he's going to talk about Cubical Pachner moves and bordisms of immersions for the main seminar. And for the pre-seminar, there will be some background going on. So feel free to ask any questions.
Okay, yeah, so I guess I can share a white.
Would be great. Oh,
okay.
Okay. That's fine.
Okay, so I thought I was just going to talk a bit about what simplicial Pachner moves are. So my talk is going to be on cubical Pachner moves, but they're better understood if you know what happens in the simplicial case first. Okay, and this is aimed toward grad students. And okay, so just to get started, okay, so sort of when we talk about manifolds, talk about there's sort of three main categories you can talk about. You can talk about topological manifolds. So these are just manifolds in the in the topological sense, and then with continuous maps. You can also talk about differentiable manifolds. So these are manifolds with a differential, with a smooth structure on them, and with differentiable maps. And then in between, you have something called a piecewise linear or a piecewise smooth. And these are what you can think of as manifolds with a piecewise linear structure on them, and then with piecewise linear maps or piecewise smooth maps. And it's the same piecewise linear and piecewise smooth. They're defined differently, but they're equivalent to each other. Okay, so in this talk, we're going to, and in combinatorics, usually you deal with this category here. Okay, so what is this category?
Oh, sorry, Gaku, mind if I ask something?
Yeah.
When you said this PL1 is between the other two, is there sort of a reason why we should see that, or?
Yeah, so I mean, this is a theorem. Well, okay, well, yeah, okay, so it's a theorem that every smooth manifold has a piecewise linear structure on it.
Okay, but it shouldn't be obvious why that's true.
I don't think it's too hard. Like,
okay.
I mean, it's not like trivial, but like I don't think it's like considered to be too hard.
Okay.
What do you mean by linear on a manifold?
Sorry.
What do you mean by linear?
Yeah, okay. That's what I'm gonna define now. Okay.
Also, are you saying that linear and differentiable are the same thing?
No, I'm saying that these two categories are equivalent to each other, and that's a theorem.
Oh, okay.
Okay. Okay. So okay. So given a topological manifold, and by manifold I mean that a manifold of dimension D means that every point has a neighborhood which looks like Euclidean space, D-dimensional Euclidean space. Piecewise linear structure, PL, triangulation. Of M is a simplicial complex. Which is homeomorphic to M. and such that the link of every face is a PL sphere. Okay, so I'm going to define what these terms mean. So okay, so a simplicial complex is a space formed by taking simplices and gluing them face to face. So that's what I'll take as my definition of a simplicial complex. And then okay, so when you have a simplicial complex, the homeomorphism class of it is unique, so it does not depend. So it's determined precisely by the combinatorics of the simplicial complex. And was the link of a face. So if sigma is a face.
By homeomorphic to M, do you mean like its union is homeomorphic to M or something like that? Or a support, that's the word.
Yeah.
Okay.
Yeah. I actually just defined it to be like the whole space, but okay, but whatever. Yeah, sure.
Well,
okay.
I mean the simplicial complex, the support of the simplicial complex.
Yeah, exactly. Yeah. Okay.
Because like the simplicial complex is like a set of simplices. So.
Right. Yeah. So if X is a simplicial complex, sigma is an element of X, so a face of X. Then the link of sigma is equal to all tau in X, such that sigma union tau is an X. So if your simplicial complex, maybe locally it looks like this around a sigma, the link would be this set of all the simplicial complex, which is a set of all of these.
So they have to be disjoint with sigma.
Yeah. Okay, sorry, I guess, so sigma union tau, I guess I should say, because of the way I defined what a simplicial complex is, I guess I should say the convex whole, or, okay, I guess that doesn't make sense either. Okay, so I mean, okay, so when you have a simplicial complex, you can think of the elements of the simplicial complex as being you can identify each simplex with the vertices of that simplex. So what this is saying is that the vertices of sigma and the vertices of tau form a simplex in X.
And they're disjoint.
Oh yeah, sorry, yeah. Okay, so all right, so this is what a piecewise linear triangulation of M is, and then but we can also start without a topological manifold. We can just say a simplicial complex which has this property that the link of every face is a piecewise linear sphere. And sorry, I defined a piece. So we can define this inductively. So a piecewise linear sphere is just a triangulation of a sphere, which satisfies this link property. And this is one dimension lower, so we can do this inductively. So if M has dimension D, and then this sphere will have dimension D minus 1, so, and then we've already defined it for that. And then sort of so then this gives a full definition of what this should mean. Okay, but we can also start from this definition. If we have any simplicial complex which satisfies this link property, then we can call this a piecewise linear manifold. Okay. Okay, so maybe I should, okay, so all right, so that's sort of the setting we're talking about. So when we talk about piecewise linear manifolds, that's what we're talking about. And now we're just going to work strictly in this category. So we're not going to sort of worry about sort of pathologies that might occur if we want to try to think about how to transfer these results to smooth or to top. Okay. All right, so I'm actually going to want to work with a slightly more general setting. So let's say a simplicial post set is a space formed by gluing simplices along unions of faces. So in the simplicial complex, the simplices can only be glued one face to one face, but now I'm going to allow simplices to be glued along multiple faces. I'm not going to allow them to be glued to themselves, but for example, you could have something like this. So this is going to be fine. And I think I'm just going probably because I'm not going to be so diligent, I'll probably just abuse notation, call this also a simplicial complex. So most people would not call this a simplicial complex.
What does that look like combinatorially? Is it just like a multiset of subsets?
So okay, so I mean, you can use this term post set. So you can describe this as a post set where each face is an element, and then so you have two maximal faces, and then each of these has 3 children, and then they share something like that. So
well, I was just thinking about
like
the definition of a simplicial complex, which is like we take subsets of the vertices, and then there's some restrictions on. So I was wondering if this could be expressed in that way, I guess.
it's not the best way to do it. So
oh, okay.
Yeah, so I mean the better way to do it is to look at all the faces and rather than just the vertices. And to
Gaku, doesn't it have 3 vertices, not 4 like you drew in the post set?
yeah, okay, yeah, sorry.
Oh, I didn't mean you had to take it all back, but I was just trying to understand if I.
Yeah,
what
it should be
post
like
set you were drawing.
this. Yeah, I drew the post set wrong.
4 edges, 3 vertices, and an empty set, I guess.
Yeah. Oh, yeah. Okay. Sorry. That line was correct. The line below that was wrong. Okay. Sorry. Yeah. I'm not gonna try to do this on the fly. So okay, I'll try to go faster. So let's. Okay. So the reason why I want to do this is so I can define what a Pochner move is. So a Pochner move is a move on a triangulation. So I'm going to just assume all triangulations are piecewise linear, which replaces, let's say, okay, a Pochner move on a D-dimensional. Okay, that replaces a subcomplex isomorphic to a subcomplex of a D+1 simplex. And then with the complement that simplex. Okay, so what does that mean? Okay, let's say I have some simplicial complex down here. So okay, so this is a two-dimensional simplicial complex, and then let's say I take these two faces here. So if I look at a three-dimensional simplex, these two faces I can identify with these, say, like these two faces here. And then the complement are going to be these two faces here. So what a Pochner move does is it replaces these two faces with these two faces. So in these, what that'll look like is it'll look like something like this. So you can imagine as I put a three-dimensional simplex on top of it, and then I sort of look above it. So instead of seeing the bottom faces of that simplex, I'm seeing the top faces of that simplex.
So can we apply a, does it have to be full dimensional? Like, I mean, to talk about a complement, right? Can we only talk about complements of full dimensional subcomplexes?
Yeah, let's say you have a full dimensional. Let's replace it as d-dimensional.
Right, d-dimensional. Yeah, I was thinking about the boundary complex of the simplex. Yeah, because I was like, how would you even define, say, the complement of a vertex? Right.
Yeah. Sorry, I should have said d-dimensional.
Okay,
so another type of Pochner move is, for example, the complement of a single face is these three faces. So if I have something like this, I could replace this face. I could replace this triangle here with three triangles that look like that, and vice versa. So I can take these two triangles and replace it, and then replace it with a single triangle. And remember, this is all topological. So even though I'm drawing it in a plane, as long as you can as long as it looks topologically fine, it's okay. And the reason why I worked in this simplicial poset setting instead of simplicial complex setting is, in general, using these moves might bring you to something that looks like this. So this just makes it a little simpler to expand our notion to these simplicial posets. Okay. So
are these Pochner moves defined on subcomplexes with complexes with like 4 or more faces, say in 2 dimensions? Like if I had 4 or more simplexes and I tried to take the complement there, does that make sense?
Okay, yeah. So no, yeah, I understand your question. So no, okay. So a d-dimensional subcomplex whose complement is also d-dimensional, I guess. Yeah. Okay. So it has to be both the subcomplex and its complement have to be d-dimensional. Okay. So the theorem is that given a topological manifold M and 2 PL triangulations of M, there exists a sequence of Pochner moves which move between which changes one to the other. And this theorem is by Pochner. So this is why they're called Pochner moves. Okay, so that's sort of the main result of these moves. So if you have any two PL triangulations in their their homeomorphic as manifolds, then you can move between them just using these Pochner moves. Okay, so that's basically all I have to say. So I mean, in the talk, I'll be talking about a cubical analog of this. So this is for simplicial complexes, but you can also talk about cubical complexes, which are same thing, but you work with cubes instead of simplices. And you can define analogously what it means for a Pochner move to be cubical. You can define analogously what a cubical Pachner move is. And I'm going to talk about, well, okay, so this theorem fails for that, but I'm going to talk about the way in which it fails and what exactly what the obstructions are. Okay, so that's all I have to say.
I guess as a simple example, is it right to say from this theorem that we can go from, say, a tetrahedron to an octahedron via a series of Pochner moves?
Yes.
Okay.
For this result, is there any sort of like canonical sequence we can take given two triangulations?
That's a good question. I don't know. I mean, at least in the proof, the proof definitely does not give one. But
the tetrahedron is actually just the same as a triangle, I guess, because you can, delete 3 of the faces using a Pochner move, like a double triangle. I mean, topologically speaking.
Yeah, I was kind of thinking if like an approach would be to like go to a common refinement in some sense to like refine it and then coarsen it again, but I don't know how, if that's like
yeah, so yeah, I mean that would work if you could move. Okay, so one thing you can do is you can use things called stellar subdivisions, and stellar subdivisions you can show are always sequences of Pochner moves. And so I think what the common proof is that is you show that two of these simplicial complexes have a common stellar subdivision.
Thanks.
Yeah. So there is going to be actually. Okay, so there is subdivision, which is the sort of the canonical common refinement of these two simplicial complexes, and that's just formed by putting the two complexes on top of each other. So this is not a simplicial complex, but it's going to be some polyhedral subdivision, your manifold, and then you can choose some triangulation of this. So yeah.
It's pretty interesting. You actually, it's not just refinement though. I mean, I think I've found a pretty simple way to get from the tetrahedron to the octahedron. And so like you start with, the basic net of the tetrahedron. You subdivide 3 of the faces using that one Pochner move, but then you have to do 3 of the reversal Pochner moves. Can I? Never mind.
Okay, so yeah, maybe that can be an exercise for the pre-seminar.
If you want to, like, there are plenty of people watching here. I'm not gonna.
Okay, are there any other questions? Well, then let's thank our speaker and feel free to unmute yourself.
Thank you.